Okay, so in the last session, we discussed this notation for permutations and also for combinations. We did some practice questions on this as well. So we have this new notation now, NPR. This was the summary that we had at the end. We said whenever the number of objects is equal to the number of spaces or places in which we have to arrange them, when they're both equal, we could use n factorial, but when they're not equal, then we generally use this notation NPR. And what that means is we want to arrange R out of n, arrange R things out of n. Now, if the number of objects is greater than the number of places, then you take that as n, and if the number of places is bigger, that is greater, then you take that as n. So whatever of these two numbers is the larger number, you take that as n, so that comes on top here in this notation. And whatever is the smaller number, that comes as r at the bottom of this notation. All right, so that's what we talked about in the last session. We also started combinations. Combinations are when the order of objects is not important. You only care about the objects which are selected or chosen. It doesn't matter in which order they are chosen or in which order they are selected. So that is unimportant in this case. This is the notation that we use for this. NCR, this means select R out of n objects, right? This is this is how we use combinations. We did some examples of this. We also learned this relationship between permutations and combination. NPR can be written as NCR multiplied by R factorial. So basically permutation is two things. In permutations, you have two things happening together. One is that you are selecting some objects, and then you are arranging those selected objects, right? So there are two things that permutation does at the same time. It selects objects and then arranges them. Sometimes if you have some conditions on selecting, you have to handle those conditions separately and then arrange them afterwards. We did an example in this as well. We also talked about what happens when you have probability coming alongside permutations or combinations. You just use that standard probability formula there. Probability equals number of favorable outcomes divided by the total number of possible outcomes. So if you're talking about permutations, you say number of favorable permutations divided by total possible permutations. And similarly for combinations, favorable combinations divided by the total possible combinations. We did an example on this as well. Now, let's say we have something like this. In how many ways can you select two letters, or let's say three letters, from A, B, C, D, E. We've got 6 letters. We want to select 3 of these letters. In how many ways can you do this? Now, generally, if all of these letters were different, we would do something like this. We would say, we've got 6 letters. Out of those 6 letters, we need to select 3. So we could do 6C3. And that in this case gives us 20. But since we have 2 letters which are repeated here, we cannot use something like this. This is not going to work. Okay, because you've got some repetition, right? Now, when we used to do arrangements, we had a particular way of handling these repetitions. We had a way of handling what happens to these identical objects. So what we did in that case was we said, if we have something like this, so if we have some repetitions, we could just divide by the number of arrangements of the repeated object, right? So we used to find the total number of possible arrangements and then then divide that by the arrangements of the repeated objects, right? So in permutations or arrangements, we could handle this directly. But when we have combinations and we have repeated objects, like in this case, combinations does not have a way of handling identical objects directly. It can't handle repeated objects directly. What you have to do in this case is you have to basically write down the different possibilities you have for the repeated object. So what you do is you think about all the different possibilities you have for that letter that is repeated, or whatever object it is that is identical. You think about all the different options you've got for that identical object. In this case, we've got A that's repeated, that's coming twice. So we would consider all the possible cases that we have for the letter A. Now, one possibility would be that amongst those three selected letters, two are A's. That is one possible case, that you are selecting two A's, all right? Another possibility could be that you're selecting just one out of the two A's. That could be another possibility. And then the last possibility would be that you're not selecting any of the A's. All right, so you'll have to make three different cases for this. You can't handle this directly otherwise. So the first case is that you have two A's. You are selecting two A's. That's the first case. The second case is that you're selecting one A. And then the last case is that you're selecting zero A's. And then you find the number of combinations, number of possibilities for each of these cases one by one. Now, when you have two A's selected, now this is already done. Yeah, you have selected two A's. Now, you've got one space left, one place left. You have to select one out of the remaining four objects now. All right, so you've selected one, you've selected two A's already, you've got one place left, and you have four options left. Out of those four, you have to select one. So in how many ways can you do this? You can do this in 4C1 ways. All right, now the rest of the letters are all different. So in that case, we could use combinations directly, but for the repeated object, you'll have to make these cases like this. All right, so the first case has 4C1 ways of doing it. Okay, let's look at the second case. The second case already has one A selected. So out of these two A's, we're saying we are using one A. Okay, so that's the second case. Now, from the remaining four letters, how many do we have to choose? We have to choose two out of the remaining four letters. So in this case, it's going to be 4C2. All right, so for the remaining four letters, we have to, from the remaining four letters, we have to choose two, that's 4C2. And then the last option is that you're not selecting any of these A's. That's another possibility. All right. So that means from the remaining four letters, we have to choose three now. So that's the last option, 4C3. Now the first case gives us 4. The second case gives us 6. The third case gives us 4 again. It could either be the first case or the second case or the third case. It's one of these three cases. So what's the total number of ways of doing this then? 4 plus 6 plus 4, that is going to be 14. So basically, in combinations, you cannot handle the repetitions or identical objects directly. Okay, let me just write that down here. In combinations, identical objects or repeated objects cannot be handled directly In this case, we need to basically make multiple cases for this identical object to find the total possible combinations. All right, so this is something that we'll have to do in combinations every time. All right. Yes, Iman, you're saying something?
Sir, in this case, we had only one letter, which was A, that was being repeated. But what if in the same
Yeah.
case we had another letter that was also being repeated?
Yeah, that's a good question. So what if you had uh, A, and then B, B, C, D, E? Now you'll have to basically make a number of different cases for this that account for all of those combinations. So for example, you could have no A and no B's. All right, so let's say you have to select three letters. One possibility could be that you're not selecting any of them. All right. Another possibility would be that you're selecting one A and that's it. Another possibility could be that you're selecting just one B. Another possibility would be that you're selecting one A. In fact, two A's, let's say. Another possibility would be that you're selecting two B's. Another possibility would be that you're selecting one A. In fact, let's say two A's and one B. Another would be that you're selecting two B's and one A. And that's pretty much it, I think. A, B. And then you have A, B, B. You could also have A, B. You're selecting one A and one B. That could also be a possibility. So you'll have to list down all of those different cases like this. All right. And then find those combinations from each of these cases and add all of them up. Generally, in almost 95, 99% of the cases that you will encounter, you'll only have one thing repeated in combinations because otherwise it becomes quite tedious like this, right? So it doesn't happen very often that you have multiple repeated objects in combinations. If it happens, then they try to formulate it in a way that you don't end up having to make a lot of cases. All right, so it'll generally be limited to 5, 6 cases at max. All right.
Okay, sir. Thank you.
All right. So this is what you need to do in combinations. Now, this basically covers pretty much all the concepts that we need to do in permutations and combinations. Now, there are a few things that come up with every single question. So we'll do them as we go along. Now we'll spend the next few classes, we're actually going to spend today and at least 2 more classes after this on doing some practice questions on this. Okay, this is the topic that requires a lot of practice, so we do need to spend some time on this. So that will be today and also 2 more classes after this, inshallah. All right, now let me start with a couple of questions from the worksheet. The worksheet is posted. You've got questions posted from that as well. You need to make sure that you are attempting them. And if there are any difficult questions, you can also let me know about them. We will be doing some of the difficult questions in the next couple of classes anyway. But you can let me know if there are any that you're not able to figure out, so I can add them to the list as well. Now I'm going to start with some that are not that difficult, they're not very difficult, so that we get up to speed gradually. We will be spending today and possibly a couple of more sessions on doing some more practice questions on this, because this is a topic that does require a lot of practice. There are some things that you only learn by doing questions, right? So you'll find out that there are some small things that they're going to come up with every single question that we will learn on the go. Now, this worksheet is uploaded on Classroom already as well, and there are questions assigned from this as well. Please make sure that you are attempting those questions as well. You can let me know if there are any difficult questions that you were not able to do, I'll also try to add them to the list that I have in mind as well. Let's start with this one. This is question number 42 from the worksheet. Let's try and do this. A committee of 6 people is to be chosen from 5 men and 8 women. In how many ways can this be done if there are more women than men on the committee? Now, first of all, we need to decide whether this is combinations or permutations, or sometimes it's both, one after the other. In this case, you see a committee of 6 people is to be chosen. All right. That's a keyword that we got for combination. And think about this, if you're choosing people, it doesn't really matter who we are choosing first and who we are choosing second. All that matters is what the end result turns out to be, who are the people who are selected, right? That's all that matters. The order is not important. So this is combination. Now we've got 5 men and 8 women, that's 13 people in total. And out of them, six have to be chosen. And there's a condition. That condition is that there need to be more women than men on the committee. Now, we have to think about the different possibilities we could have in this case. So we've got some men. How many are there? There are 5 men. And then we've got some women. Women are 8. So there are 5 men and 8 women. Now, what are the possibilities that you have? You want the total number to be 6, okay? Since there have to be more women than men. One possibility could be that you've got no men and 6 women. That's a possibility, right? So there could be the committee could have all women, right? So that's 6 and 0. That's one possibility. Another possibility could be that you've got 1 man and then 5 women. And then you could have 2 men and 4 women. And that's it. Because if you have 3-3, then the condition is not met. You want more women than men. These are the 3 possibilities that you have in this case. All right. Now, how do you do the calculation? You're saying the first possibility is that there are 0 men and 6 women. So how do you select them? You have to select no men out of 5. So 5C0 and 6 out of 8 women. So that's 8C6. So the first case would be 5C0 into 8C6. Now the second case is that you're selecting 1 man and 5 women. So that's 5C1 into 8C5. And then similarly, you've got 5C2 into 8C4. These are the 3 options that you've got there. All right. Now, what does the first one give you? Let me just try this. 8C6. If I were to do 8C6, this results in 28. So the first one gives us 28. 5C1 into 8C5, that gives us 280. And then finally, the last one gives us 700. Okay, we can find the total, and the total turns out to be 1008 in this case, right? Because it's either the first case or the second case or the third case. Add all of these different possibilities. Horizontally here, we are saying there have to be 0 men and 6 women. So we multiply them. 1 man and 5 women. So we have to multiply them. But vertically, we're saying there's only one of these cases that's possible. So we add them together. All right, the total turns out to be 1008. That's the number of possible committees we could have given this condition. All right, that's the first part. Now let's look at the second part. Now the second part says, in how many ways can this be done if the committee consists of 3 men and 3 women? So we know the number of men and women, but there are 2 particular men who refuse to be on the committee together. Now those 2 people they don't want to be on the committee together. So let's say these two men were M1 and M2. Now these people, they can't be on the committee together. All right. So you can't say that both of them are part of this, uh, total of 6 people. Now, again, you have to think about the cases that you've got for this. You could have one of the two, but not both at the same time. Or you could also have none of them selected in the committee at all. All right, so all of those possibilities are there. Now let's list down what are the possible cases that we have. One possibility could be that you are selecting M1, but not M2. Another possibility could be that you're not selecting M1 and selecting M2. That's another possibility. And the third possibility would be that you're not selecting any of them. All right, these are the cases that you've got. Now, remember, what's the total number of men? The total number of men is 5, and the total number of women is 8. Now, we've got 5 total men, and out of those 5 men, we have 2 who are M1 and M2. Now, the condition is on these 2 people that they can't be on the committee together. All right. Now, what if M1 is selected and M2 is not selected? What are the options that we have for the remaining people? Now, you see, let's say the rest of the people were M3, M4, and M5. There are 3 men who are left after this. We want a total of 3 men, right? That's what it says in the question. We want a total of 3 men. Now, if you're saying that M1 is selected, but M2 is not selected, now out of those 3 people, we already have 1 person selected, right? So we know this person is already selected. How many places do we have left on the committee for men? We've got 2 places left. And where those 2 people are going to come from now? They're going to come from these 3 remaining people, because we know that M1 is selected and M2 is not selected. So there's no choice there's no choice that we have to do for these 2 people now. We have 2 places left in the team after M1 is selected, and those 2 places have to be filled by 2 of these 3 men. So in the first case, we say the number of ways this could be done would be 3C2 and not 4C2. That's very important to understand. It's not 4C2 because we know that M2 is not selected. All right, so that's decided. It's decided that M1 is selected and M2 is not selected. So the decision about both of these people has already been made. The option is only for these 3 people. Out of these 3, we need to select 2 more. Okay, so that's why we've got 3C2 here. What about women? There's no condition on women. There are 8 women, and we have to select 3 out of them. That's just going to be 8C3. And in fact, that's going to be the case for all of these cases here as well. The number of ways of choosing women, it's going to be 8C3 because there's no condition for women. But now let's look at the second case for men. Let's see what happens there. Now, this is exactly the same as the first case. It's just that now we are not selecting M1, but we are selecting M2. So 1 out of the 3 people is already selected. We've got 3 people left, M3, M4, and M5, out of which we need to select 2 more. So this is again going to be 3C2. All right. And then finally, we are saying both of those 2 men are not selected. If both of them are not selected, that means we have 3 people left. Out of those 3, we have to select all 3. So the number of ways we have for doing this is going to be 3C3. So the first option is 3C2 multiplied by 8C3 because we're saying we are selecting 2 out of 3 people and 3 out of 8 of these people. Okay. In the second case, we're saying we're selecting 2 out of 3 men and 3 out of 8 women. So we multiply these two as well. So we multiply all of them. And then since only one of these cases is possible at one time, we add these together. All right, so now we can do this calculation and see what this turns out to be. The first one is giving me 168. The second is exactly the same, so that should also be 168. Now, what about the third one? 3C3 into 8C3. This turns out to be 56. These are the three possibilities that we've got. And now, since it could be any one of these three cases, what we do is we add these cases together. We're saying it's either the first case or the second case or the third case. So we add those possibilities and the total turns out to be 392. And that is the answer. That's the number of ways in which you can select this committee, given this condition is met. All right, let's have a look at the next part. Now it says one particular committee, it consists of 5 women and 1 man. So now the committee is chosen. All right, we know there are 5 women and 1 man. In how many different ways can the committee members be arranged in a line if the man is not at either end? All right, now let's think about this. There are 6 people. We have 5 women and 1 man. And now we have to arrange them, right? So this is permutation. This is arrangement. How do we think about this now? There's a condition that we have to meet, that the man cannot be at either of the 2 ends. Now remember, what did we used to do for arrangements? We used to have this boxes representation. We could use that here. So how many boxes do we have? How many places do we have? We have 6 people. So we have 6 boxes to represent them here. Now the condition is the man cannot be at any of the 2 ends. It cannot be here. The person cannot be here and also not be here. Now, how many options do you have for that 1 man? You've got 4 options for that, right? So that man could be here or here or here or here. So if you were to place that male in one of these boxes, how many options do you have? You got 4 options for that. All right. Or you could say 4P1, however you want to do it. You got 4 places and you have to arrange 1 person. That could be 4P1. 4P1 is the same thing as 4. So you could write either 4P1 or just 4 because there are 4 options. It's pretty obvious there. All right. So there are 4 options for the man because that man cannot be at the ends. He cannot be here or here. All right. So there are 4 options for the man. That's done. So the man is placed in one of these 4 boxes now. Let's assume that man is placed here. Let's say he was placed here. Now we've got 5 women left. In how many ways can those 5 women be arranged? Now, you've got 5 places left and there's no condition now. You've got to arrange these 5 women in these 5 boxes. How many options does the first woman have? 5 and then 4, then 3, 2, and 1. Or you could also do the other way around. How many options do you have for the first box? 5, then for the second box, 4, then 3, 2, and 1. So that is just going to be 5 factorial or 5p5. That's the same thing. This is what we have. This is going to be the number of arrangements that we get in this case. All right, 4 options for the man. Once we have placed that man in one of those 4 boxes, then we have 5 factorial ways of arranging the women in the remaining 5 boxes. And that is going to give you the result 4 times 5 factorial. That turns out to be 480. And that's your solution. All right. This is what we had to find in this third part. Okay. I hope that makes sense. Let's move on. Let's look at another question then. If there are no problems with this, we will try another one now. All right, let's do this one, question number 36 from the worksheet. Let's try this. Okay, so a shop has 7 different mountain bicycles, 5 different racing bicycles, and 8 different ordinary bicycles on display. A cycling club can select 6 of these 20 bicycles to buy. In the first part, it says how many different selections can be made if there must be no more than 3 mountain bicycles and no more than 2 of each of the other types of bicycles. All right, so we've got 7 different mountain bicycles. Now, do notice this word different. So these cycles are not identical, they're all different. Okay, so you're not going to consider them repetitions, or you're not going to consider them identical. You have 5 different racing bicycles, and then you have 8 different ordinary bicycles. So there are a total of 20 bicycles. Out of these 20, a club selects 6 to buy. Now, how many different selections can be made given these conditions? You can have at most 3 mountain bicycles. No more than 3 means you could have 3, but not more than 3. We're looking for the different selections. If there can be no more than 3 mountain bicycles and no more than 2 of each of the other 2 types of bicycles, right? That's the condition that's given. Now let's list down the total number that we have for each type. For mountain bicycles, we have 7. For the racing bicycles, we've got 5. Okay, so what we have to do is we need to find how many different arrangements are, how many different selections can be made given these conditions, right? So what we need to do is we need to figure out the different options we can have if these conditions are met. Now, this is the total number that we have for each of the 3 bicycles. We've got 7 mountain bicycles, 5 racing bicycles, and 8 ordinary bicycles. And we have to list down the cases that we have. Now, since the mountain bicycles cannot be more than 3, one possibility could be that we have 3 mountain bicycles. And then what about the other 2? We could have, let's say, 2 racing and 1 ordinary. Another possibility could be that we have 3 mountain bicycles and then 1 racing and 2 ordinary. Now, there's no other case with 3 mountain bicycles because if I were to make it 0 and 3 or 3 and 0, that would violate this condition. We can't do that because the other 2 types of bicycles, they can't have more than 2. All right. So these are the only 2 options that we get with 3 mountain bicycles. Now, what if we had 2 mountain bicycles? With that, we could have 2 racing bicycles and 2 ordinary bicycles. These are the 3 cases that we have, and that's it. We don't have any other case apart from this. Now, let's figure out the total possible selections we could have from this. Now, the first case is that we're selecting 3 mountain bicycles out of 7 and 2 racing bicycles out of 5 and one ordinary bicycle out of 1. And so on for the other two. We got 7C3 into 5C1 into 8C2 for the second case, and then we have 7C2 into 5C2 into 8C2 for the last case. All right, we evaluate each of these cases and then we add them together and see what that turns out to be. Now, let me just try this quickly. The first case, let's see what that gives us. The first case gives us 2,800. The second one gives us 4,900. And the last one gives us 5,880. Now we just need to add all of them up because it could be any one of these cases. And that turns out to be 13,580. That's the total number of possible selections we could do in this case. All right. That's the first part. Let's look at the second part now. Now, the second part says, the cycling club buys 3 mountain bicycles, 1 racing bicycle, and 2 ordinary bicycles. So now the cycles are bought, right? So they are purchased already. You have 3 mountain, 1 racing, and 2 ordinary. That's given. Now these are parked in a cycle rack, which has a row of 10 empty spaces. How many different arrangements are there in the cycle rack if the mountain bicycles are all together with no spaces between them? Okay, so mountain bicycles are all together with no spaces between them. The ordinary bicycles are all together, are both together with no spaces between them. And the spaces are all together as well. Okay, so the 3 mountain bicycles have to be together, the 2 ordinary bicycles have to be together, and the remaining spaces, the empty spaces, they have to be together as well. Now, remember the representation we used to use for this. We have to arrange objects. We could use the boxes representation for this. Initially, it says we've got 10 empty spaces in which we have to park those bicycles. All right. 6 of them are going to be bicycles now, and 4 are going to be the empty spaces after that. Now, initially, we would have 10 boxes for this, right? 4 empty spaces and 6 bicycles. So initially, we would have had 6 boxes that represent each of those places. Now, it says the mountain bicycles have to be all together. There are 3 of them. So we could say, let's merge 3 boxes and make them 1. And in that 1 box, you could put M1, M2, M3. These are the 3 mountain bicycles that you have. Now remember, they're all different. So you could write M1, M2, M3. They're not identical. Then you have 2 ordinary bicycles. They have to be together as well. So you merge 2 boxes and put ordinary bicycles there. You could have O1 and O2 for this. There are 2 ordinary bicycles here. They're also different. You have 1 racing bicycle that could come here. That's just 1 box because there's only 1 cycle. And there are 4 remaining spaces, and it says the spaces also have to be together. So for spaces as well, we say we should make 1 single box. We should have 1 single box for spaces as well. All right. Now, empty spaces, we could say these are all E's. But now, think about it. These are just empty spaces. All right. So they are going to be identical. They are not going to be different. Okay. Empty spaces are all the same. So they are identical. Now, in how many ways can we arrange all of this? We start from these outer boxes, first of all. How many boxes do we have here? We've got 4 boxes. In how many ways can we arrange those 4 boxes? We could arrange those 4 boxes in 4 factorial ways. All right. That's the arrangements that we have for these boxes. So mountain bicycles could go to the right, racing could come here, empty spaces could come here, and so on. So all of the different arrangements that you have for these boxes, That is 4 factorial. Now, let's think about each of these boxes one by one. So you've got one box that has mountain bicycles, and how many ways can you arrange those mountain bicycles inside that single box? You've got 3 mountain bicycles. You have 3 factorial for them. All right. Then you have 2 ordinary bicycles. They are different as well. They could change their place as well, switch their places as well. There are 2 factorial ways of arranging those ordinary bicycles now. All right. Then you have racing bicycle. It's only one. That's 1 factorial. It doesn't matter if you write that or not. And then finally, you've got the 4 empty spaces, 4 E's. And how many ways can you arrange these E's? Well, they're all identical. It doesn't really matter. Even if they were to change their position, it's all the same. They're all identical. All right. So we don't have to consider arrangements for these empty spaces as well. We can just ignore them. If we were to consider them, we would do something like this. We would say 4 factorial, because there are 4 empty spaces, but they're all identical. So we also have to divide by 4 factorial because of that. Eventually, it just gets canceled out, right? So it doesn't matter if we do this or not. It's just going to get canceled anyway. All right. So you can just ignore them since they're all identical. You don't really have to arrange them at all. You just find the total from this and see what that turns out to be. 4 factorial into 3 factorial into 2 factorial. That's 24 times 6 into 12. That should be 500 something. Let me just check. No, 24 into 6 into 2, not 500. 24 into 12. Yeah, so that's 240, 248. So that gives me 288. Okay, so that's the result that we get from the second part. That's the total number of arrangements given this condition is met. Okay, let's look at the third part now. The third part says, how many different arrangements are there in the cycle rack if the ordinary bicycles are at each end? If the ordinary bicycles are at each end, remember there are 3 mountain bicycles, 1 racing and 2 ordinary. Now the condition is, in the third part, the ordinary bicycles are at each end of the bicycles and there are no spaces between any of the bicycles. So all the cycles are together now. All the cycles are together. There are no spaces between the bicycles. And the ordinary bicycles are at each end of the bicycles. Now think about this. How many parking spaces do we have? We've got 10 of them. We've got 10 parking spaces. Let's represent those 10 parking spaces initially. Okay, these are the 10 parking spaces that we have. Now, the ordinary bicycles have to be at each end. Now, you might think initially that one could be here and another could be here, but that's not possible because remember, there can't be any gaps between the bicycles. So if you had ordinary bicycles at the ends, then there would be gaps between bicycles. So it says there are no spaces between any of the bicycles. So all the bicycles, all 6 of them have to be together. So essentially what we need to do is we need to have all the bicycles together. How do you do that in boxes representation? We used to put them in one single box. So you could merge 6 boxes and make them one. So in this one big box, we're going to have 3 mountain bicycles, M1, M2, M3, and O1, O2, and R. However, remember there's also a condition for this actually. The condition is that the ordinary bicycles are at each end of the bicycle. So that's a condition that we've got to that we've got to account for within this big box. And what's that condition? Let me have another box here in which the cycles could move around. Ordinary bicycles have to be at the ends. So if one of them comes here, let's say O1, the second has to be here. These are the positions that we have for the ordinary bicycles. They have to be in these two boxes. Okay. And the remaining ones, we have one racing and 3 mountain. They could come in any of these places that we have in the middle. There are 4 places. They could be arranged in any way after that. All right. So ordinary bicycles have to be at the ends. So you could have one ordinary here, another here. And then the rest of them, the other types, they are in the middle. And what about these 4 spaces? These are 4 empty spaces. So we have 4 E's that are going to come in these boxes. Okay. Now it doesn't say anything to the effect that the empty spaces have to be together or they could be separated or not. There's no condition on empty spaces, so we just consider them as separate boxes. We could have a case like this as well, that we have one empty space on the left, and we have cycles in the middle. We have cycles in the middle, and then we have 3 empty spaces on the side, or 2 at both ends, right? So all of that is possible. There's no condition on that. So we've got 4 E's there. That's what the situation looks like. All right. Now, how do we find the number of arrangements in this case? We start from the outer boxes, first of all. How many outer boxes do we have? We've got 5 outer boxes. So for 5 outer boxes, we've got 5 factorial. For the 5 outer boxes, we have 5 factorial. But now, out of these 5 boxes, 4 have E's in them. And all of those E's are identical. All right. So we are arranging these 5 boxes. One of them is one big box, and then the remaining are these 4 boxes that have 4 E's in them. So that's 5 boxes in total. The total ways of arranging those 5 boxes is 5 factorial, but out of those 5 boxes, 4 are identical. So we have to divide the 4 factorial to account for those 4 E's that we have. All right. So this is the number of ways in which we can arrange those 5 outer boxes. All right. Now let's think about what's happening inside this big box. Now, first of all, we have the 2 O's, right? One here and one here. They could also switch places, right? One could be O1, O2, and another could be O2, O1. So we have to consider their arrangements with each other. There are 2 of them, and there are 2 places. We could say that is 2 factorial. So that's the number of ways in which we can arrange the ordinary bicycles, 2 factorial. And then we're left with these cycles in the middle. There are 4 of them. They're all different. And there are 4 spaces in the middle for them. And how many ways can we arrange those 4 bicycles? We can arrange them in 4 factorial ways. All right. So it's 5 factorial over 4 factorial into 2 factorial into 4 factorial. Just evaluate this and see what this turns out to be. And this is going to give us 240. Okay, I hope that makes sense. We will end this here. We'll do some more practice tomorrow, inshallah. If you have any quick questions, you can let me know. Otherwise, we'll do some more questions tomorrow, inshallah. Okay? Allah Hafiz.